The world's oceans are a vast, mysterious expanse, covering over 70% of the Earth's surface. Beneath their waves lies an invisible armada of submarines, stealthy, silent, and equipped with some of the most advanced weaponry ever created. These vessels glide through the depths, often beyond civilian oversight or accountability, carrying out missions that range from reconnaissance to strategic deterrence. Nuclear-powered ballistic missile submarines, capable of annihilating entire cities, coexist alongside attack submarines that stalk their targets from the shadowy ocean floor, ready to disrupt enemy surface operations. The presence of these machines is a constant undercurrent in global naval strategy, with incidents like the detection of a Russian Kilo-class submarine in the Philippines' exclusive economic zone last year promptly escorted out by the Philippine Navy, highlighting their elusive nature. Every major naval power maintains a fleet of these submarines, investing billions of dollars not only in their development but also in technologies designed to detect and neutralize them, creating a high-stakes technological arms race beneath the waves. Nowhere is this competition more intense than in the seas surrounding Taiwan, where China is constructing what has been dubbed the Great Underwater Wall of China. Since 2016, China has operated underwater sensors in strategic locations, including one at Challenger Deep, the deepest point on Earth, and another off the coast of Yap, Micronesia. Positioned near Guam, a critical U.S. military outpost in the Pacific, these sensors lie along a primary entry route into the South China Sea. For nearly a decade they have tracked U.S. naval movements, and China is now expanding this network to envelop its entire maritime border, aiming to make it impossible for submarines to enter its territory undetected. This capability could thwart an amphibious invasion of Taiwan before it even begins, reshaping the strategic calculus in the region. The Great Underwater Wall is a massive undertaking, with an estimated cost of $300 million. China has openly showcased its progress, broadcasting videos of the installation process and displaying scale models on national news. The system relies on clusters of acoustic sensors, each comprising sonar arrays and hydrophones. The sonar arrays are active devices that emit sound pulses and listen for return signals, with 3 arrays connected to a primary gateway for precise triangulation of any object's position within a 160-kilometer range. Hydrophones, on the other hand, passively listen for intruders, making it difficult for submarines to detect the sensors themselves, as the sonar pings are audible only to their targets. Powered by onshore facilities delivering 10 kilovolts of high-power direct current through undersea cables, the sensors are linked by optical fibers for rapid data sharing and analysis. Intriguingly, the system includes a charging dock for underwater drones, likely intended for maintenance but potentially capable of powering autonomous drones designed to attack submarines, a glimpse into the future of naval warfare. Detecting submarines is only the first step. Countering them requires a multifaceted approach. The United States, for instance, relies on the Lockheed P-3 Orion, a submarine hunting aircraft in service for over 50 years. Equipped with a range of anti-submarine weapons, including the Mark 50 torpedo, the P-3 is designed to target deep-diving submarines. The Mark 50's propulsion system is a marvel of engineering, using a lithium fuel and sulfur hexafluoride oxidizer, a rare combination that produces combustion products with a smaller volume than the reactants, allowing exhaust to be stored on board without pressure buildup. The heat from this reaction generates steam in a boiler, driving the propeller, while the steam is cooled by surrounding water in a condenser and recycled. This system eliminates an exhaust wake, making the torpedo harder to detect. However, the P-3's primary role is reconnaissance, not attack. Its most distinctive feature is a magnetic anomaly detector, MAD, housed in a long pole extending from its rear stabilizer, designed to detect minute disturbances in the Earth's magnetic field caused by a submarine's ferromagnetic hull. The Earth's magnetic field, typically around 50 microns less, is disrupted by the magnetized steel hulls of submarines. Detecting these anomalies requires extraordinary precision, as the disturbances can be as weak as 0.001 nanotesla's 50 million times fainter than the Earth's field. Early magnetometers used a simple design with a coil-wrapped metallic ring, where opposing coils canceled out in the absence of an external field. In the presence of a magnetic field, a slight bias in the core allowed measurement of the field as an electric current. Modern systems, like the ASQ81 magnetometer, take this further by exploiting the interaction of infrared light with helium atoms. At a precise wavelength of 1085 nanometers, helium atoms absorb light, jumping to a higher energy level. In a magnetic field, the Zeeman effect splits these energy levels into three, with the energy gap proportional to the field's strength. By shining a laser through a helium cell and measuring light absorption with a photodiode, the system can detect changes in the magnetic field. A radio frequency pulse tuned to the energy gap repopulates the middle energy level, causing a dip in detected light that reveals the field's strength. With three detectors aligned along the X, Y, and Z axes, the system maps the magnetic field in 3 dimensions, allowing the P3 to pinpoint submarines, though it must fly at low altitudes, often 500 feet or less, following a grid search pattern to maximize detection chances. Submarines, however, are not defenseless against such technologies. The Soviet Union, for instance, achieved a remarkable feat in the 1960s by constructing submarines with titanium hulls. Titanium, a diamagnetic material, has a minimal effect on magnetic fields, making these submarines nearly invisible to magnetic anomaly detectors. The Soviet Alpha-class submarines, first spotted in 1969, were small, nuclear-powered vessels just 79 meters long, with a reserve buoyancy 3 times higher than American. Unlike the ancient Great Wall, built to repel invaders like the Mongol hordes, this modern marvel is designed to detect even the stealthiest submarines. Highly reflective surface, both indicative of titanium construction. This material's strength-to-weight ratio allowed the submarines to be lighter, stronger, faster, and capable of diving deeper than their steel counterparts, reaching speeds of 40 knots while submerged. The challenge of welding titanium, which oxidizes rapidly when heated, was significant. The U.S. faced similar issues when building the F-14 Tomcat's titanium wing box, requiring a custom electron beam welding device to remove oxygen from the weld area. Speculation abounds about how the Soviets managed this on a shipyard scale, with some suggesting they hermetically sealed entire indoor shipyards, though CIA documents cast doubt on this. More likely, they developed localized sealing methods, a testament to their engineering prowess. The U.S. deemed titanium submarines too costly and complex to pursue, but the Soviet achievement spurred the development of the Mark 48 torpedo, capable of 55 knots and powered by Otto-Fuela stable, non-flammable monopropellant. Its axial flow, liquid propellant swashplate pump jet engine, with 6 pistons driving counter-rotating propellers, made it a formidable weapon, guided by active and passive sonar and a wire connecting it to the launching submarine's superior sensors. The battle for submarine supremacy extends beyond sound and magnetism. In 2023, China launched 4 satellites equipped with synthetic aperture radar, SAR, to monitor sea traffic in the Western Pacific, capable of detecting submarines by their surface wakes. SAR achieves high resolution by creating a virtual antenna through the satellite's motion, sending overlapping radar pulses and combining their echoes to produce detailed 3D maps. This technology, which requires an antenna length proportional to the radar's wavelength and the satellite's altitude, allows detection of subtle wave patterns caused by submerged submarines. Meanwhile, the future of underwater warfare is shifting toward autonomous drones. Northrop Grumman's Manta Ray, visible on Google Maps, exemplifies this trend. These drones, powered by underwater charging stations like those in China's acoustic wall, eliminate the need for human crews, allowing for designs with reinforced plastics instead of metal, reducing magnetic signatures and near-silent electric motors, minimizing acoustic detection. Capable of anchoring to the seafloor in a low-power listening mode, these drones could form a great swarm, rendering traditional submarines obsolete. This technological race is not without its challenges. Keeping pace requires innovative tools like OnShape, a cloud-based CAD platform that eliminates the need for software installation and ensures all team members work on the latest design version. Capable of handling compute-heavy tasks like finite element analysis in the cloud, Unshape's government version complies with EDAR and EAR regulations, making it suitable for defense projects, such as designing secretive drone submarines. Whether for professional or hobbyist use, such platforms highlight the importance of staying ahead in a world where technology evolves rapidly beneath the waves. The invisible armada of submarines, countered by ever-advancing detection systems, underscores a relentless pursuit of dominance in the ocean's depths, where stealth, innovation, and strategy collide in a silent, unseen battlefield.